Hello guys, welcome back to my channel. So today we'll start a few problems on Poisson distribution. So I think in the previous video you should have seen the PMF, CDF, mean and variance of a Poisson distribution. Now before moving on to the problems in Poisson distribution, I'd like to tell you some few important points about Poisson distribution. Okay. So imagine that I'll tell you with an example. Okay, imagine that there is a wire. Okay, so this is a wire. Let's say of some n length, whatever. Okay, now if the wire is split between let's say sub intervals. Okay, let's say this is an interval, this is another interval, this is another interval, so on. There are totally t intervals. Okay, and now this part is called a sub interval. Okay, this is another subinterval, this is another subinterval. When you speak of this subinterval, we can tell that these subintervals are of a small length delta t. Okay. Why does delta t? Delta means small. Okay. So when you take a wire of length t, and it's not exactly length t, it's just split into t real numbers. Okay. Let's say 1, 2, 3, 4, and to t real numbers. Okay. Now each subinterval will be of a length delta t, which is very small length. Okay. Now if you consider that delta t as a small length of subinterval, now we'll assume that this delta t will tend to 0. Can you remember something when we saw in the Poisson distribution? We told p will tend to 0 and n will tend to infinity. We are coming to that only, okay, eventually. Now, if delta t will tend to 0, okay, which means what? This interval is so small such that the probability of occurring a flaw, okay, if there's an error that is occurring in the subinterval, okay, which means a bit error, okay, we'll come to that problem in in a few minutes. I'm telling about getting an error. We saw in binomial distribution also, right? The probability of getting one error, okay, a bit error, whatever, a flaw, let's say generally a flaw, in that small interval is very low. Okay, let's take that it's only that's only probability of one just one flaw. Okay, uh, uh, that is the probability of more than one event in this subinterval is actually 0, which means what? There's only one flaw that can take place in a subinterval. Okay, that is first important point. Okay, the probability of more than one flaw. Okay, more than one flaw in a subinterval. Okay, in a subinterval is almost 0, which means what? There can only be at most only one flaw in a subinterval. Okay, just this is one assumption. Okay, the second assumption is the probability of one event in a subinterval tends to lambda delta t by t. What is this? Okay, now if lambda is let's say the mean flaws per subinterval. Okay, lambda is mean flaws. Okay, now if the wire is of a length, let's say it's split into t intervals, and each subinterval has a length delta t, what is the total number of intervals? Just t by delta t, right? If a wire is of 10 centimeter, and each when cut into pieces of each 2 centimeter each, what is the total number of pieces? 10 by 2, which is 5, right? Similarly, t real numbers are there, split into delta t intervals. Total number of intervals is actually t by delta t. This is what n, because there are totally n intervals in this wire of each of length delta t, and there are two t real numbers. Okay, now delta lambda t by t is what? Lambda by t by delta t, and this is what? Lambda by n. Can you see what is this? This is nothing but p, right? Np is equal to lambda. That's what we saw yesterday in the previous video, right? P is equal to, sorry, np is equal to lambda, right? So this is one another assumption. Okay, the event in each subinterval is independent of other subintervals, which means if there's a flaw occurring in, this is very important point. Okay, if there is a flaw occurring in this subinterval, that is independent of a flaw occurring in another subinterval, in any subinterval. Okay, these independent events. So flaws are independent. Understood? If these three conditions are satisfied, then we call that as a Poisson process. Okay, all these three conditions are satisfied, we call them as a Poisson process. Understood? This is what I wanted to tell. Okay, now let's move on to the question. Okay, so very easy only. This you remember, delta t by t by delta t, that is nothing but n, and that is p. So from this only we told, right, when your delta t will tend to 0, which means what? Which means what? N will tend to infinity, because see, t by delta t is there, no? Here we told the delta t will tend to 0, which means t by delta t will tend to infinity, which means n will tend to infinity, which means p will tend to 0 again, because this, if n is infinity, p will be 0. And that's what we told in the previous video. I forgot to tell about the Poisson process, so I'm telling here. Okay, now first question. For the case of thin copper wire, suppose the number of flaws follow a Poisson distribution with a mean of 2.3 flaws per millimeter. Determine the probability of exactly 2 flaws in 1 millimeter of wire. Okay, it's very easy only. So, our Poisson distribution they've given, and the lambda is what? 2.3 flaws. I'm writing F for flaws per millimeter. Okay, so if there is a some n length of wire, for 1 millimeter, there is a possibility that there are 2.3 flaws. Okay, that is the mean average number of flaws. Okay, now the probability of exactly 2 flaws in 1 millimeter of wire, which means that the random variable is nothing but getting flaws. That is a random variable. Okay, so getting 2 flaws, which means x is equal to 2. This is nothing but what? What is the PMF of random Poisson distribution? E power minus lambda into lambda power x by x factorial. Correct? Now e power minus 2.3 into 2.3 power 2 by 2 factorial. If you calculate this, what will you get? You can check it out. Okay, it's nothing but e power minus 2.3 into lambda power x by x factorial. Okay, some value will come here. You can please tell in the comments. Okay, now determine the probability of at least one flaw in 2 millimeters of wire. Okay, here this is important. Okay, now here they gave the mean as 2.3 flaws per millimeter, so it is for 1 millimeter, and they're asking to determine the probability of exactly 2 flaws in 1 millimeter, which is fine because the mean is also given for 1 millimeter, and they're asking the probability also for 1 millimeter. But now they are asking the probability for at least one flaw in 2 millimeters, which means the your mean will change. Okay, now the lambda will be this 2.3 flaws for 1 millimeter. So for 2 millimeters, it will be 2.3 into 2 is nothing but 4.6. 4.6 flaws per millimeter. Okay, so now probability of at least one flaw. Okay, so x is greater than 1, which is what? You cannot calculate 1 plus 2 plus 3, right? So same concept as we discussed in binomial distribution also. 1 minus p of x is equal to 0 plus p of x is equal to 1. Okay, now 1 minus p of x equal to 0 is what? E power minus 4.6 into, so I think I missed here minus. Anyways, if you do the square, it'll do the same thing, but okay, minus 4.6 power 0 by x factorial was 0 factorial. Okay, plus e power minus 4.6 into minus 4.6. uh sorry, why did I write minus here? Sorry guys, sorry. Minus will not come. My into 4.6 power 1 by 1 factorial. Okay, now if you calculate this, you'll get the answer. Okay, so in this question, what important thing we saw, for one lambda, if they give for 1 millimeter or 1 meter, whatever, in the question you have to see for what they're asking the probability of flaw. Okay, if they ask for probability of flaw in the same value as they gave the lambda, it is okay. You can directly calculate like this. But if they change the the base unit, okay, that is, if they change the average value, then you have to change accordingly. Okay, so that's all. So now let's go to the second question. Okay, this is very easy only for just to tell the CDF and PDF, sorry, PMF purpose. I've taken this question. So suppose X is a Poisson distribution with a mean of 4. Okay, so they've given lambda as 4. I think there's a bit of lag here. Just let me know. Okay, so P of X is equal to 0 will be what? E power minus 4 into 4 power 0 by 4 factorial. That's all. Now, P of X less than equal to 2. It's nothing but P of X is equal to 0 plus P of X is equal to 1 plus P of X is equal to 2. You can calculate it. I think you can do this as a homework. Okay. Now, C is what? P of X is equal to 4. This is nothing but E power minus 4, 4 power 4. Sorry guys, this is X factorial, no? So this will be 0 factorial. So this will be 4 factorial. Okay. Now P of X equal to 8. Nothing but E power minus 8. Sorry, E power minus 4 into lambda power X, which means 4 power 8 by 8 factorial. Understood? That's all. Simple guys. Okay. So next question. Okay, this is a nice question. The number of telephone calls that arrive at a phone exchange is often modeled as a Poisson random variable. Assume that on the average there are 10 calls per hour. Okay, which means what? Your lambda will be 10. Just read the question and write this. Okay, 10 calls per hour. Okay. Now, what is probably there are exactly 5 calls in 1 hour. So for 1 hour only, they give the mean also, which is the lambda. They're asking the probability also for 1 hour only. So there's no problem. So probability of exactly 5 calls means what? X is equal to 5. Can you calculate this? Easy. E power minus 5. Sorry. E power minus 10 into, what is lambda again? 10 power 5 by 5 factorial. Understood? Now, B part. What is the probability that there are 3 or fewer calls in 1 hour again? No problem. Since they give 1 hour, you need not change the lambda's value. 3 or fewer calls, which means X is less than equal to 3. Take P of X equal to 0 till X equal to 3 and do it. Again, this is a homework. If you want answers, I'll give it in the description. Okay. Now, see what is the probability that there are exactly 15 calls in 2 hours. Okay, 15 calls in 2 hours. See, now they changed the lambda. Now the lambda for this part will be, what is lambda for 1 hour? 10. So what is for 2 hours? 20. That's all. 20 calls per 2 hours. Okay, now exactly 15 calls. No problem. P of X is equal to 15, which is equal to E power minus 20, not 10. Okay, lambda power X, 10 power, sorry, again, see, I'm doing mistake. 20 power 15 by 15 factorial. Understood? Very easy. Okay, now we'll go to the last question for today. If you want more questions also, you can tell me. Okay, I can take some questions and solve. When a computer disk manufacturer tests a disk, it writes to the disk and then tests it using a certifier. The certifier counts the number of missing pulses or errors. The number of errors on a test area on a disk has a Poisson distribution with lambda equal to zero point 0.2. Okay, there is some disk. Okay, and it first writes to the disk and it tests using a certifier. Okay, some test certifier, some algorithm or something. Okay, the certifier which is used for testing, it actually counts the number of missing pulses or missing error or basically errors. Okay, that that follows a Poisson distribution. Okay, that is point two. Okay, what is the expected number of errors per test area? What is expected means, expected number means what? It is lambda only, no? E of x, nothing but lambda only. But they've given lambda's value, so that is the answer. Simple. What percentage of test areas have two or fewer errors? So P of x less than equal to 2. Okay, sorry, which is equal to P of x is equal to 0 plus P of x is equal to 1 plus P of x is equal to 2. Okay, now only thing you have to do is find the probability and you will get some value, let's say x. Okay, now multiply that x with 100 to get x percentage, because they ask what percentage of test areas. I think you'll get 99 point something. Okay, I just calculated but now I'm not doing it. Okay, so I think some 99.8 something you'll get, so that report in a percentage. Okay, otherwise they'll reduce half mark or something. Okay, so simple. Okay, now, what is the thing you have learned it today? The only important thing you've learned it is mostly to first calculate the probability based on the the PMF e power minus lambda into lambda power x by x factor. That is fine. Another thing is that the means value. Okay, the mean, see for what they've given the mean. Okay, for what, what for 1 hour they've given, or for 1 millimeter they've given. See that and see the question what they're asking for. Okay, accordingly manipulate the means value. And that is one more thing, and this part is important, guys. Which part? This Poisson process. Okay, there is a question, seeing they've asked that, so similarly one question was there and they asked, for the next 10 minutes what is the probability or something like that. Okay, but and they've asked one question that if that 10 minutes whatever is happening, maybe the flaw, maybe the telephone call coming in next 10 minutes, whatever. Okay, they ask question like, uh, that 10 minutes whatever is going to happen next 10 minutes, should it be continuously happening or it can happen in 1 minute first and take a break and again 1 minute. Okay, but nevertheless the important point to know here is, it is independent. If it doesn't matter if it happens continuously or it happens discretely, which means 1 minute first and then break, then 2 minutes like that, because every sub process is independent. That's what Poisson process says. Okay, Poisson distribution obviously follows Poisson process. Okay, the flaws are independent. See, this point is very important. Okay, flaws are independent, which means what? The sub intervals are independent of each other. So this sub interval doesn't have to do anything with the sub interval. Okay, so it can be anything. That's a very important point. Okay, so I think that's all about Poisson distribution. The next we will see about geometric distribution. If you have any doubt, you can please ask, and if you want more questions also, you can tell in the comments. We can solve. So thank you guys for watching. I'll see you in the next video. Okay, bye.